Okay, thanks a lot, Manuel, for the very nice introduction. I wasn't expecting that. Okay, so I will speak about my recent work on the sigma k Loewner-Nirenberg problem in collaboration with Maria Delma Gonzalez, Yan Li, and Jinggang Song in the last 4 or 5 years. Okay, so the plan of the talk is that I will spend some time talking about some background material, and then I will describe the main results and maybe some key ideas in. Okay, so let me start with a classical theorem in 2 dimensions, the uniformization theorem. So it says that the universal cover of any Riemannian surface is conformally equivalent to either a disk, the plane, or the sphere. A consequence of that is that if you have a planar domain omega, such that the complement of it contain at least 2 points, then the universal cover of omega is conformally equivalent to the unit disk. Now, suppose that omega is one such domain, and let F be a covering map from D into omega. Then for any such covering map, we can project the Poincare geometry from the disk to omega, and we obtain, in particular, a complete and conformally flat metric on omega with negative curvature. So we call these hyperbolic metric on omega. So let's take a few examples. So let's say that AR is an annulus where the modulus of Z is less than R and bigger than 1 over R. So this is still in 2 dimensions. Yeah? Then the hyperbolic metric on this annulus can be written as lambda squared times dz squared, where lambda of Z takes this particular form. So some constant depending only on the size of the annulus times this function 1 over Z times cosine of pi log Z over 2 log R. So you can see that when Z is going to R or 1 over R, then this cosine factor here becomes 0. So the function lambda blows up. Now, if we look at the Euclidean circle mod Z is equal to R, and we look at the length of this circle with respect to this hyperbolic metric, so we call it LR, then you can calculate this to be pi square over log capital R times cosine of the previous ratio that we saw before, pi log R over 2 times log R. So here is a plot of it. On the horizontal line, this is the log R, and on the vertical line, we have the length of that Euclidean circle. So we see that it's symmetric around log R equal to 0. So at the boundary of your domain, then the length of this Euclidean circle is infinite, and is minimum exactly at log R equal to 0. So this is at that point you have a geodesic circle. Now another example, one can do explicit calculation is when you look at the puncture disk. So D star. So this one here, the hyperbolic metric is given by this lambda is 1 over Z log of 1 over Z. Then we can do the same plot on the horizontal line. We have the log of the Euclidean radius, and on the vertical line we have the horizontal the hyperbolic radius. Then we see that the length of this circle blows up on at log R is equal to 0. That means that as Z is going to 1, and the length go to 0 as Z is going to 0. So this behaves slightly differently from the previous case. So we should keep in mind that at the boundary of this domain here, at the origin, it's a singular boundary. The boundary is not a curve; it's just a point there. So it behaves slightly differently. So just to fix idea, later in the talk, when we talk about domain, we will not deal with the situation in this example. We will deal with a situation that mostly like in the previous example, when the boundary are regular hypersurface, so of codimension 1. Now, there has been a lot of work even in the 2D case, and I just choose a couple of things here that I think might have some relevance later on. Say if omega is a convex domain, a hyperbolic domain, so it's a simply connected one that is equivalent to a disk, then if we look at the hyperbolic metric and we look at the function lambda, then by the work of Caffarelli and Friedman and Minda and White in the 80s, we see that these function lambda has certain convexity properties. So for example, log lambda is convex, or 1 over lambda is concave. So I suspect that this will have some relevance in the study in high dimension. I don't quite know yet, but I suspect it has something, so I just put it here. Okay, so in this talk here, I will talk about a higher dimensional analog of that. Let me start first with the result by Loewner-Nirenberg in the 70s. So suppose that omega is a domain in Rn where n is now 3 or higher. And for simplicity, we just assume that the boundary of omega is smooth. Their work applies to more general setting, but just to fix idea, we keep in this talk the simple setting of a smooth boundary. Then their theorem asserts that there is a unique smooth positive function u on omega, such that if we take, I think there's a typo here. So it would take u raised to the 4 over n minus 2, and then we multiply that with the Euclidean metric delta. Then we obtain a complete and of course conformally flat metric on omega that has negative scalar curvature. From a PD point of view, so this means that this Liouville equation, so Laplacian u is equal to n times n minus 2 over 4 times u to n plus 2 over n minus 2 on omega has a positive solution that blows up at the boundary. And after Loewner-Nirenberg, there has been a lot of work, and I do not try to put everybody here, but I just put some people here just to give you a feeling that the work continue up to the latest one that I'm aware of was last year. So it's still quite active work doing in this area. Okay, so that's about the Loewner-Nirenberg problem. So in this talk, I will talk about fully nonlinear generalization of this problem. And the problem I will consider is of this type. It's a sigma k function of the eigenvalue of a matrix. I would try to put it equal to 1, and I look for a positive solution, and I will continue to impose that u goes to infinity at the boundary. So first, let's just explain the notation. So k would be an integer between 1 and n, and sigma k is the kth elementary symmetric function. So if you give me a vector lambda in Rn, then I would check this sum over here, and then I call that the sigma k function of lambda. So this matrix A superscript u is called a conformal Hessian of u. The expression, the precise expression of this matrix I will show on the next slide. But maybe for the talk, the particular form is not so important. All I want you to keep in mind is that at the leading order term is the Hessian of u modified by some power of u that is critical for the with respect to scaling, and then the rest are lower order term. The precise lower order term is important in my work, but for the sake of the talk, we don't need to care too much about it. And it has the property that when k is exactly equal to 1, that means that the sigma 1 of lambda is just the sum from lambda 1 to lambda n. Then the equation we look the equation 2 above here is exactly the equation considered by Loewner-Nirenberg. Okay, so as promised, here is the expression of the Southern tensor or the conformal Hessian. So A superscript u is minus 2 of n minus 2, and then u raised to this power minus n plus 2 of n minus 2 of Hessian of u, and then plus 2 terms that are first order in u and quadratic in u. So now if we see that if we take trace of this matrix, then the last term here will give you a 2n, and then that would cancel with what with the second term here, and we recover exactly the Laplacian, and so that's why we obtain the Loewner-Nirenberg problem. And this expression comes from conformal geometry. So AU is, if we think of it as a matrix, then it is nothing other than the 1, 1, the entry of the 1, 1 southern tensor of this conformally flat metric u to the 4 over n minus 2 delta. And okay, so throughout the talk, I will always assume that whenever I talk about the sigma k equation, I will assume that the eigenvalue of the conformal Hessian belong to the so-called gamma k curve, which is defined as the set of lambda in Rn, such that all the sigma j function is positive for j in between 1 and k, including 1 and k. So this is one type of the equation. So in some literature it's referred to as the negative type problem. Another kind of ellipticity condition is to impose that lambda of AU rather than lambda of minus AU is in the gamma k curve. But we will not discuss that problem in this talk. Okay, a closely related problem is called the sigma k Yamabe problem, but this one is posed on a manifold. So the question is to ask to find on a given closed Riemannian manifold MG a positive function u, such that the sigma k of the eigenvalue of the southern tensor of the new conformal metric u to the 4 over n minus 2g is equal to 1. So is equal to a constant. And again, for in this case here, we're imposing that the eigenvalue of the southern tensor is in the gamma k curve. Okay, so it's just some literature about the problem. So for our model, the matrix A superscript u start with is a modified sort of Hessian term with a bunch of first order term. If we just ignore all of that and we just retain the Hessian, then that problem was first considered by Caffarelli, Nirenberg, and Sprague in the 80s. In the context of conformal geometry, it was started by Vyachelovsky around 2000, and then followed by many people. I put up a list here, and I apologize if I ignore someone. It wasn't intentional. I just go through my paper and select a few that I quoted in the last 2 or 3 papers that I wrote. Okay, so let me go a little bit more into the background, but more on the mathematical side rather than more on the literature. So the nature of the problem is a non-uniformly elliptic problem. A different or a difficulty perhaps in treating the equation comparing to the case in the when we imposed that the eigenvalue is in the positive gamma k cone, is that in the case that we're looking at now, the local Hessian estimate, depending only on C0 or even C1 bounds, are not known. Some people believe it's false. So, however, recently in a joint work with my student Jonah Duncan, who is at Johns Hopkins now, so we prove a pointwise Hessian bounds depending on W2p for large enough p, and for k bigger or equal than 2, then the range that we have p here will even imply C1. So we assume quite a lot. but here we have a regularity theory. So we start with W2P and then we bootstrap it to W2 infinity. Now, another problem that has been considered in the literature as well is to replace the modified Southern tensor by the so-called modified Southern tensor AGT, where T is allowed to be less than or equal to 1, and with T, so there's a typo here, so T equal to 1, T equal to 1 being the problem we are considering. So for T less than 1, the problem is somewhat better behaved. So if we just ignore all of the theory, if we just look, for example, at ellipticity, then even though the problem is still non-uniformly elliptic, it actually has better behavior from below. So the analogy is if we look at a linear problem, then the ellipticity from below is bounded by a fixed non-zero constant, but the bound from above could go to infinity. Whereas for T equal to 1, we don't have that problem. It could go either to 0 or infinity from either side. Okay, so the first result in this context is due to Gursky and Vierklovsky in this negative case in around 2003, where they show that the sigma k Yamabe problem on a manifold for the modified Southern tensor with T strictly less than 1 has a unique C2 positive solution. So now, so in the last couple of years, so Yan and I observed that if we use, instead of the notion of classical solution, but we use viscosity solution, then the result that Gursky and Vierklovsky obtained can be used to deduce the existence of a Lipschitz viscosity solution in the case T is equal to 1. So that more or less saying that the sigma k Yamabe problem on a closed Riemannian manifold is solved. So I will not define precisely what is this notion of viscosity solution, other than just saying that it's some sort of generalized solution where in the definition we only need continuity to make sense of the equation. However, although we say that it's solvable, in that setting when T equal to 1, we don't know uniqueness. So equivalently, we could say that if there is a C2 solution, then all solution, then if we know that if the solution is C2, then it's unique. But so far, we only know that it's Lipschitz, and we know that there is a Lipschitz solution. We don't know if it is the unique solution. Okay, so let's go back to our setting where we're discussing the Loewner-Nirenberg problem when the domain we have is in Rn. So here's an example, a simple example. So suppose that omega now is a ball in the Euclidean space, and we look at the equation of solving sigma k of the eigenvalue of minus the conformal Hessian is equal to 1. Then an explicit solution can be written down. And if we take this function u, we raise it to the 4 over n minus 2 and multiply with the Euclidean metric, then we obtain exactly the Poincare metric on the ball. So clearly that metric has constant curvature, and in particular has constant sigma k curvature. Now, when omega is instead of a ball, is being now an annulus, say in between two number A and B, where A is positive and B is finite. Then in 2005, Chang, Hang, and Yang study all rotationally symmetric of such equation, and they show that there is no C2 rotationally symmetric solution when K is bigger than 2. On the other hand, in the case when K equal to 1, one can even write down explicitly what they are in terms of some integral. and they are all regular. So the starting point for our project started in around 2017 or 2018, when Maria, Yan, and I proved the existence and uniqueness of a continuous viscosity solution. So suppose now that n is bigger or equal than 3, as always in this talk, and omega is a domain in Rn, and for simplicity, we assume in the talk that it's bounded with smooth boundary. Then the sigma k Loewner-Nirenberg problem has a unique continuous viscosity solution. Moreover, we can show that the solution is locally Lipschitz, and at the boundary, it behaves in the way that we expected. That if we take the distance to the boundary, raised to the power n minus 2 over 2, and multiply it with our function u, our solution u, then as x is going to the boundary, that quantity there approach a constant that depends only on the dimension n and the number k in the sigma k problem. Okay, so the way that we maybe if I rewind it a little bit. So here is the theorem of Gursky-Vyachelovsky. The way that thing works here is to relax first from a uniform elliptic problem, a non-uniformly elliptic problem, to a problem that has better ellipticity, and then somehow get C2 solution there. And if we use viscosity solution, we can go back to the k t equal to 1 and obtain a Lipschitz solution. The approach that we do, we use in this, in the proof of this is slightly different. So it's Perron's method, basically. So the starting point is a comparison principle, which I proved together with Yan and Bo Wang in earlier on. So once we have a comparison principle, we can then use the Perron's method to first solve for the a problem where instead of putting infinite boundary value, we put a finite boundary value using Perron's method. And for that, we're going to use a lot of barrier that comes from the particular solution on ball that I show on the previous page. So that gives existence and uniqueness. To prove uniqueness, then we rely on the comparison principle and the precise blob rated boundary that we state in the theorem. And to prove the blob rated the boundary, then again we use comparison to standard solution on balls. And to prove Lipschitz regularity, then we rely on something moving sphere method. Okay, so the treatment in this problem is slightly different from the context on manifolds. One can also ask the question about Loewner-Nirenberg on problem on manifolds. So that means on domains in a Riemannian manifold setting. Then this agenda will run into some problems. So we at the moment we don't have a comparison principle to work on general Riemannian manifolds. And to use Perron's method, we would need to create a large class of barrier in a way, and that's also missing in Riemannian setting. Okay. So let me then now move on to discuss the regularity issue, which is the main part of the talk that we that I state in the title, that the solution are not differentiable. So now, when in the case that Loewner-Nirenberg consider, that is when k equal to 1, then when the domain inside the domain the solution is smooth. Now, we said earlier that on analyze, Chang, Han, and Yang showed that there is no C2 rotationally symmetric solution. And by the theorem that we showed 2 slides ago, we know that for any such any domain, in particular on an annulus, we have a Lipschitz solution. So the following theorem precises the nature of irregularity of the solution on an annulus. So the solution U is not C1 across the hypersphere modulo of x is equal to root AB, when AB are the limit of the annulus. And away from this singular sphere, the solution U is smooth. Now, if we look only to one side of the sphere, then the solution U is C1 1 over K, but no better in each of the sides. So this means that the singular set is a regular hypersurface. In here, it's just a sphere. So this begs the question. Okay, this is very particular to the case of annulus, right? Because you say that, okay, we have an annulus. Our equation is rotationally invariant. We also have uniqueness. So that means that any solution of this equation has got to be rotationally symmetric. And so it reduced somewhat into a study of an ODE, a complicated one though, unfortunately, but it's still an ODE. Then, so by the work of Chang, Han, and Yang, we already know that there is no C2 solution. And then somehow the content of the theorem is the precise location of where the singular point is. Okay, what about the general case? So that in the general case, we proved the following thing with Yan and Jingang Song this year. So let n be the same, so 3 or higher, and omega is a bounded domain with smooth boundary. So let's suppose that k is 2 or higher, and let's suppose that the boundary omega is disconnected. So the disconnectivity of the boundary is essential in our proof. Then the sigma k Loewner-Nirenberg problem has no positive solution in C1. So putting it differently, the local Lipschitz solution that we obtain in the theorem with Gonzalez and Yan is not a differentiable solution, even though it's the unique one in class of all continuous viscosity solutions. So how much time do I have?
Let me see. 20 more minutes? About 20 minutes. Yeah.
Yeah. Okay. So let's see where. Okay. So let me maybe explain something that go into the idea of the proof. So maybe it's good to remind ourselves of the picture in the 2-dimensional setting. So this is the picture that we drew for the length of the Euclidean circle with respect to the hyperbolic metric on an annulus. So right, so we see that the length of that circle blows up at the boundary of the domain, and then in the middle there's a point where the length is minimal, and by symmetry at this point here, so that means that at radius r equal to 1, we have a geodesic. Right, so that means that the hyperbolic metric on the annulus open up to infinity at the end, and then in the middle we have a geodesic. Okay. So the proof in the high dimension somewhat built on this intuition. So if we suppose that now we are in the situation in high dimension, if we suppose that the solution U behaves like a negative power of distance, in this precise form. So there is a constant times the distance to the power minus n minus 2 over 2. And let's suppose that we can develop this to up to any precision we like, in particular up to the first order, say. Then if we look at the surface that lie as a distant delta away from the boundary, then we can calculate the asymptotic expansion of this of the mean curvature of this surface as delta is going to 0. Then you see that it would be at leading order, it would be a constant, a positive constant, and then times a term that is big O of the distance. So in particular, this would be positive, right? Strictly positive. So that sort of that is consistent with this picture here. As we move inside, the length of the Euclidean circle got smaller and smaller. So that means that the length of the geodesic circle is decreasing, right? So that's that means that the mean curvature is positive. So now that means that if our metric, if the solution U is, say, if it is nicer than say differentiable, say, and if boundary of omega is disconnected, then at each component of the boundary we have these mean convex surface. So we could use them as barrier to construct a minimal hypersurface sigma inside. And if the dimension is bigger than A, the hypersurface could have some singular set in it, but the codimension would be at least 8. Okay. But in the work that I did with Yan earlier on, we know that when K is bigger than 2, there is an obstruction for existence of a minimal surface. So let me show you the statement for this obstruction. So let omega be an open subset in Rn, and let sigma be a C2 closed embedded surface in omega, and nu being a continuous normal field along sigma, so, or you could say the sigma is oriented. And now if U is a positive C2 function such that the eigenvalue of minus the conformal Hessian is in the cone gamma 2, then we have this differential inequality that relate the Laplacian of U with respect to the Laplacian of U with respect to the metric induced on sigma, the mean curvature H of the surface sigma with respect to the Euclidean metric, and the mean curvature of the surface sigma with respect to the conformal metric U to the 4 over n minus 2 times the Euclidean metric, and the surface gradient of U. Okay. So now, if we assume that we have a surface sigma, say smooth for the moment, such that the mean curvature of U with respect of sigma with respect to the conformal metric is 0, then the second term here is trivial. So this term here drops out. So I would have that Laplacian of U will be bigger or equal to the sum of the third and the fourth term. So these are non-negative terms. But if sigma is a closed surface, then that's impossible unless unless U is a constant and then H is 0. But we know that in Euclidean surface there is no closed minimal surface. So that would give us a contradiction if right, if the mean curvature of the surface sigma is 0 with respect to the conformal metric. Okay, so that's basically the rough picture, right? So if we go back to this slide, so basically this is the picture in 2D, right? If everything is nice, then at the boundary, the length of the geodesic circle decreases. So at some point it will saturate at a minimum, and we have a geodesic here. So in 2D, there's no contradiction here. But in high D, if this picture stay the same, then near the boundary, the area of these hypersurface will decrease, and at some point we will form a minimal surface. And when K is 2 or higher, we cannot have a minimal surface inside the manifold. That is the rough idea of of the proof. So let me comment on how to make that a real proof. Okay. So first of all, in the obstruction lemma, we assume that U is C2. Okay, you can say that, okay, by arguing using Wick notion, we can make it work for U in C1. We could say that, okay, we assume in the obstruction lemma that the hypersurface sigma is C2, but in general, in the construction of minimal surface, there might be a singular set. But because the singular set has relatively small dimension, the integration by part trick could still work and get a contradiction. That's not an issue. I mean, it's something we have to do, but that's more on a technical point. Now, the main part of the proof is to justify the mean curvature estimate, to say that if we look at these surface as we move away from the boundary, the mean curvature of sigma delta is positive. And for that, we need gradient estimate near the boundary. And at this point here, we run into a philosophical difficulty, because if we look at all the available work on gradient estimate in the literature, all of them are a priori, and we assume as a starting point is that the solution is only C3. Whereas here, in our context, we only know that it is Lipschitz. We don't know. We don't have more derivative to differentiate the equation to do the Pogorev method. And in a way that the proof for all of those estimates go is somehow basically you look at the linearized operator and then you rely on some kind of uniform or strict ellipticity of the linearized operator to run such an estimate. But even if we assume, right, so just for the sake of inspecting the argument, let's say that we assume for granted that our solution is C2 near the boundary, and we have all the asymptotics we need, and you plug into the equation, then you see immediately that such requirement for ellipticity is just not working in a way. Okay. So that basically is an obstruction, a philosophical obstruction. So in a way that it says that, you know, if it is going to work, we're going to need a new idea. But nevertheless, we made it work. So let's say that omega is UB as what? So omega is our domain, and U is the Loewner-Nirenberg, is the solution to the sigma k Loewner-Nirenberg problem. And we can show that there exists a delta. The delta will depend on omega and U, such that in near the boundary, right? So when the distance function to the boundary is less than delta 1, then the distance times U to the 2 over n minus 2 is going to be smooth in that neighborhood, away from the boundary. And if we look up to the boundary, then it has some limited regularity. So it would be in Cn minus 1 gamma for any gamma less than 1. And in fact, moreover, if we look near the boundary, we can have a polyhomogeneous expansion. So this is an expansion as power of D and log D. So it looks quite mouthful what this is, so I will not explain too much what it means, but it's more or less like a generalized Taylor expansion near the boundary. Okay. So when k equal to 1, so that means in the Loewner-Nirenberg setting, so such expansion was obtained by Anderson, Crusoe, and Friedrich and Maggio in the early 90s. And they even obtained it on Riemann setting. So they call it the singular Yamabe equation. For k is 2 or higher, our result is a boundary regularity result. So we do not presuppose that the solution is regular. Instead, we obtain as a consequence of our theorem that near the boundary, the solution is regular. So that means that even though globally the solution could fail to be C1, if we just restrict our attention to the boundary, it is actually smooth. Now, in the expansion, if we look at the expansion of d to the d of x times u to the 2 over n minus 2, then the regularity of this quantity at the boundary is equivalent to the vanishing of the coefficient Cn1. So if I flash it over, so right, so the first n term in the expansion are purely power of the distance, and then the next one, the n plus 1 term, is going to be in terms of the distance times a log of the distance. So now what we see is that if this term here vanish entirely, then we can develop this series here without having a log term in it. So that means we have a power expansion in terms of the distance alone, and that implies that this function here is regular at the boundary. Is C infinity at the boundary. So for k equal to 1, recently, 5 years ago, so Gover and Wandren and Graham independently found a characterization of the vanishing of this coefficient Cn1 using a conformally invariant energy. So in particular, when n is 3, then their energy is the Wilmore energy. So what they found is sort of a generalization of Wilmore energy. So in our context, we for k bigger than 2, we also have the phenomenon that, you know, the regularity of this function here depend on the vanishing of that, but we don't have such a conformally invariant characterization of this coefficient. Now, on the technical point of the proof, so if we just look at the first n plus 1 term, so right, so if we develop the power series up to we collect all the power that we have at the beginning, plus a possibility of having a d to the n log d. And if we just only care about this estimate in C0 sense, so that means we only care about upper and lower bound of the difference of the left and the right hand side, then we can robustly apply the techniques in Anderson, Krusher, and Friedrichs, and also in Vygotsky, Street, and Warrens in a related context. We will obtain this C0 estimate. So the novel part of our treatment is to bootstrap this to a gradient or even Hessian estimate. And for that, we need to put it in a way to apply a result of Savin in 2007 to get that. So let me briefly explain. I think I still have some minutes. So let me say in very quickly what it is. So first of all, instead of working with the variable u, we just use a different variable. And so we just rewrite it as the sigma k of the eigenvalue of a matrix here, where the leading part is now the Hessian. And we introduce this functional here, okay? So W would be, our solution W would be 1, so that G of W is 0. And suppose that we are doing estimate, right? We're doing boundary estimate. So let's say that we fix a point x naught on the boundary and we do estimate there. So we set up axes so that this point x naught is just the origin, and the xn direction is pointing toward the interior of omega. Now, if we do that, then it's a fact that we have g of minus log xn is equal to 0 on the upper half space. So this is just the fact that on the upper half space, we have the Poincare metric, and we just unwrap this, and this minus log of xn just corresponds to the Poincare metric on the upper half space. So we have a reference solution in this. And so then it's natural to compare, right? So because W behave as the minus log distance to the boundary. So now if we look near the origin, then log of the distance to the boundary is closely, is almost as if we are looking at log of xn. And so, but then we introduce this sort of renormalized variable. W hat is W plus log xn, and we look at the equation it satisfies. Then we just write out, follow our nose in a way, and we put out a different equation where now it's still a sigma k type equation, but the matrix involved is this matrix S hat now is x dependent. So the leading part is xn to the square times the Hessian of W, right? So in a way that we start with an equation that doesn't depend on x, and now we have an xn dependent, and then this xn here degenerate as we go to the boundary. And because of the way that we write it, g hat at 0 is definitely 0. And one can check that g hat is elliptic near 0. And what is of an essential point in the proof is that somehow this g hat here is scaling invariant. So if we rescale w hat to w hat r at x is w hat of x over r, then g hat of w hat r is also 0. It's just the rescale of g hat of w hat. So now, because we already had the C0 estimate, right? So remember that we say that we can obtain a C0 estimate like this. And if we use that information in this notation, then we have that this rescale variable w hat r is going to be less than C over r. So in particular, when r is large, this one here is going to be 0. So here, that means that this w hat r is a perturbation of the trivial solution of g hat that we have here. And so we have we can then appeal to a theorem of Savin on perturbation of small perturbation of solution to elliptic PD to say that this w hat r is EC2 near the bound, EC2 in a specific location, and if we unwrap it and return to the variable u, we obtain that it's EC2 near the boundary. And once we are at that level, then we can develop the full asymptotic expansion using methods known before, with only one slight twist that I think yeah, there's only one small twist in the argument that is different from the case before, is in the existence of this coefficient Cn0 here that I will not go into. I think it's a more technical point than a novel point. The novel point is the application of Savin's result using this renormalized variable. Okay, so I think it's a good time for me to wrap up, I think. So I will end it with two open questions. So at this point here, we know that if our domain has a disconnected boundary, then the solution is not regular. So then the natural question is that for what domain do we have a smooth solution? For example, say if we have a uniformly convex domain, then does that lead to a smooth solution? And I think the kind of discussion that was done in the work of Caffarelli and Friedman or Minter and White in terms of the convexity of the domain, the relation between the convexity of the domain and the convexity of the conformal factor lambda, or in that context they usually call the hyperbolic radius. I think that will play some role here. I have some vague idea, but I don't think I want to say anything further than that. But maybe more interestingly, to suppose that, okay, we have a domain omega and the solution is not regular, then from a PD point of view, it would be interesting to understand the singular set. So say that, okay, we have a singular set, it's unavoidable. What can we say about a singular set? And does it contain any geometric information that is relevant in geometric analysis? I will end my talk there and thank you for your attention.